I'm going to be talking about a problem where the problem is one instance of something that's a little more general. And I'll also be talking about an R package for a particular solution approach. But at the end of the talk, I will mention other packages with complementary approaches and sort of higher level messages about how this problem, although we're thinking about selection specifically, if we're thinking about data science at a high level, the problem generalizes to using the same data at different points of the data science pipeline. So if we're using the same data to both decide what questions to ask and then answer those questions, that would be an example of the type of problem that I'm talking about. So this is work which is, or this talk will be based on work that I have with a number of co-authors and a lot of other work that I'm talking about their work as well, because of the sort of general audience here, I wanted to talk about this whole area, not just my specific research in this area. So these are some of my co-authors, and this is an area that's still got active research happening in it with papers being published, and the R package is still under development and being updated. So I'm not going to reinvent calculating integrals, but I'm also going to try to not reinvent regression. So I'm going to instead call regression artificial intelligence and say it's been around since the 18th century or the 19th century. The prototypical problem that I'll talk about in this talk will be about regression modeling, but the higher level ideas about answering questions using the same data that you've used to decide what questions to ask, those higher level ideas are there, whether you're thinking about regression or something else. So regression as a method for predicting some outcome variable using other prediction variables has been around for centuries, but it hasn't been around for that long. The methods to do inference for regression, so maybe 1 century. So 2 centuries over here, 1 century over here. And this is a sort of typical thing that we see in data science, that we often come up with ways to model data and predict using these models and stuff before we figure out how to analyze whether we can trust those ways of predicting things. So in early 20th century, William Seeley Gossett, also known as Student, and Fisher had a lot of correspondence with each other where they were working out how to calculate things like hypothesis tests and intervals for the coefficients in a regression model. This is a excerpt from a paper published by Fisher, which is at the time people were using chi-squared tests for goodness of fit to check if the modeling assumption and the data that they had were kind of consistent with each other. And it turned out that when people were doing these calculations, they weren't calculating the degrees of freedom for that test correctly. And so Fisher figured out the correct way to find out what the degrees of freedom were. And he's talking about that here. And it's kind of interesting. He's saying that the values of P have been exaggerated. It is to be feared that in many cases, wrong conclusions have been drawn from the values of P obtained. So if you're familiar with kind of the current present day debates in statistical methods about using p-values and whether or not there's any problems with using p-values, those questions have been around since the very beginning of hypothesis testing. And in fact, before people even knew how to do hypothesis tests for the regression coefficients. So this is the historical kind of background of the type of problem that I'm going to talk about. And I'll be a little specific and show some mathematical detail before going into some examples of the R package. But here's a 1-slide hypothesis test review just to say very concretely what the specific example I'm talking about today will be. So we're looking at a regression model, which we know is a very sophisticated high-dimensional artificial intelligence. And we're going to think about 2 different types of tests, hypothesis tests, that we could do for the parameters in such a model. So we could test coefficients in this model. We could, for example, check the null hypothesis that a given coefficient is 0. And we designed these tests with the first goal in mind of controlling type 1 error. And the type 1 error is the probability, assuming that null hypothesis is true, that we reject it. So that would be that's the probability of a type 1 error. Rejecting the null hypothesis when it's true is a type 1 error, and we want the probability of that happening to be less than some predetermined significance level. And we usually construct tests this way by forming a test statistic for this coefficient. And we can compute the p-value for this test by looking at the observed value of the test statistic and then looking at the probability under the null that we would see something at least as extreme. So this is basically the machinery that Fisher was writing about in 1922. And we know how to do this using, for example, the t distribution for regression coefficients. I won't go into as much detail about goodness of fit tests, so I won't write down mathematical details for those. But the idea for those tests are the null hypothesis is that the modeling assumption you've made, for example, the modeling assumption of this linear model with certain distributional assumptions about the errors, that modeling assumption fits the data. So that would be the null hypothesis. So for a goodness of fit test, rejecting the null hypothesis would mean that the model does not fit the data. So some of the modeling assumptions might have been wrong, and we should really think about a different type of model. So these are the two types of tests that I want to think about. But again, like even if you're a Bayesian, you don't do these specific types of methods, you can still think about what types of properties you want your inference tools to have. And the types of problems that I'm going to illustrate with these methods are problems that you should still be worried about, even if you're a Bayesian and you're not using p-values as your primary methodology. Okay, so this is the type of problem we're going to think about. And to look at an example, let's consider an example where the null hypothesis actually is true, and our model is very simple. We just have one predictor variable. So here I've generated data where the outcome variable and the predictor variable are both just independent normal random variables. So the slope is actually 0. The null hypothesis is true. And I fit a linear model using my trusty LM function in R, and I can look at the p-value for the test for the predictor variable, and it's 0.6. So that p-value being larger than 0.05, I would not reject the null hypothesis. And the point of the frequentist guarantee that we're hoping to have with our null hypothesis testing method is that if we were to repeat this many times, for example, 1,000 times, that we would not reject the null hypothesis too often. And indeed, we can check. If we repeat this 1,000 times, we only end up rejecting the null hypothesis 60 out of those 1,000 times. And if we chose a different significance level, instead of 5%, if we chose 1%, then we would want to reject the null hypothesis only about 1% of the time. So on this slide, everything is fine and good. This is how things should work. This is how the test was designed to work. So this is great. Now let's see, let's think about how this could become a little more complicated. So on the previous slide, I just had one predictor variable, one outcome variable. You look at real data sets and you usually don't find that level of simplicity. You usually find many predictor variables. And you might want to choose from among a candidate set of many predictor variables, a subset, so that you can have a simple linear model that doesn't have too many coefficients in it. There are various reasons you might want to do that. For example, you might not have that many observations, and you couldn't even do least squares regression if you have more predictors than observations. So you would like to select a small subset of predictors, so you have more observations than predictors, and you can do least squares regression. That would be one reason you would like to do this. Other reasons are you just don't know which predictors you should put in the model at all. You have no sort of prior knowledge about which things would be predictive of why. You want to just use the data to pick which predictors to put in the model. There are a number of methods, algorithms for doing this automatically for us. So for about a half century, people have known about and used forward stepwise as one possible algorithm. And what that does is it starts with an empty model and adds one predictor at a time, choosing from the set of candidate predictors the one that's most correlated with the outcome. A little more recently, there's some other methods, other algorithms that people have proposed, including the Lasso by Tibshirani, which minimizes the squared error like least squares does, but it then penalizes the coefficients. So this penalty term means that when you minimize this, you choose coefficients to minimize this, you're trying to have small prediction error, but you're trying to do it at a low cost in the size of the coefficients. And this algorithm tends to have nice properties. For example, it usually gives you a sparse solution, meaning that the vector beta will have few entries that are not zero. So we can think of it as a method for selecting a subset of predictors, those predictors which have coefficients which are not zero. We use this, this penalty parameter here, lambda, to determine how much penalization we want to do on the coefficients. If lambda is larger, then we end up shrinking the coefficients towards zero. For large enough lambda, the minimizer would just be the zero vector. If we let lambda become smaller, then we're penalizing the coefficients less, and we can get closer to something like the least squares solution if that is defined. Okay, so these are two types of algorithms we might think about for choosing predictor variables in a regression model. Let's see an example of one of these algorithms in action on a particular data set, just to illustrate. So in this data set, this is the candy ranking data set from the 538 package. There's a number of variables which are attributes of different candy, like does it have chocolate, how much sugar does it have, stuff like that. And there's also a variable which is we can think of as a measurement of how popular that candy is. So let's build a model to predict how popular some candies are based on their attributes. But we don't know a priori which attributes should be predictive of popularity, so let's let some algorithm choose them for us. The other attributes in here are, like, does the candy have caramel in it? Does it have nougat? Is it a hard candy or a bar? So there's like 11, I think, predictor variables in this data set. And it can be tough to think about the meaning of a coefficient in a regression model with 11 variables in it. So let's try to let this algorithm pick a regression model with hopefully fewer predictor variables in it. So we have a simpler model to think about. So let's run forward stepwise regression. So we use the step function in R to do that. And what we find is that it picks these 4 predictor variables. It says that candies having chocolate, being a hard candy or a bar, and then the price are the variables which are predictive of the popularity. And then we've got, in this column, the p-values for these coefficients. So it looks like basically the bar one is the only one which is not significant at the 5% level, and otherwise they're all significant. So these results look pretty nice. And we're looking at this candy data set just because it's kind of simple and it's easy to understand, but you could imagine doing something like this in some other setting, like healthcare. You're doing something like a genome-wide association study where you've picked which genes are predictive of some healthcare outcome, something like that. And you've got these inferences and you're ready to publish these results, right? We've got a model which predicts the outcome. We've got our p-values for the predictors in this model. And should we then go and publish this is the next question. So there is a problem with this somewhere. And the problem is, on the previous slide, I had actually replaced the outcome variable with just pure noise. It wasn't the popularity of the candy. It was just pure noise. So the algorithm managed to find variables which could predict pure noise, and the tests then told us that those variables were significant. So that's the problem. This is an illustration of the problem that we're going to try to address in this talk. And the problem is selection bias. Even though the outcome variable was just noise, by looking for correlations with many potential predictor variables and then finding the ones that had the highest correlation, we ended up with values of predictor variables which seemed significantly correlated with the outcome, even though we knew that the outcome here wasn't really correlated with them. So it's that selection, that search among many possible candidates, which makes it so that the hypothesis test method isn't valid anymore. So Fisher developed the hypothesis test method in a setting where people didn't have these algorithms for picking variables automatically. They instead had only the predictor variables that they wanted in their data set. They had to probably collect the data themselves. So those hypothesis testing methods are implicitly assuming that the hypothesis you want to test was chosen without looking at the data. You collected that variable and you knew you were going to test that variable. That kind of classical methodology, it's very rare to be in that sort of scenario now when people have really large data sets and they are not using one specific model that they chose before looking at the data. They're usually using the data to pick the model. So this means we're kind of in trouble if we want to use things like confidence intervals and hypothesis tests, if we use this classic methodology, which can give us really misleading looking results when we've combined it with model selection. So here's another example to illustrate this selection effect. In this example, I'm looking at the largest out of 5 null effects. So I generate 5 random normals that have mean 0, and I look at the largest out of the 5. If I repeat that many times and I look at the distribution of the largest out of those 5 things, then we can see that that distribution does not match the standard normal distribution. So if we're doing something like selecting the most predictive looking effect out of a subset of, say, 5, then we can't use the standard normal distribution to test the significance of that effect. If we did so, our type 1 error rate at a 5% significance level would be about 25%. So that's bad. That means the test statistic method that we want to use does not control the type 1 error, which was our main goal for using it. So this problem, both the previous example and this example, comes under many various different names you may have heard, like the winner's curse or overfitting. But the one that's most relevant to the examples I'm talking about here is selection bias. Another example of this, kind of unrelated, a different version of regression related to one of the previous talks. We heard about some autoregressive processes earlier today. In this one, we can think about time series data where the model that we're going to choose is the order of an autoregressive process. So I've plotted here 2 example autoregressive processes. The top one is an AR1 and the bottom one is an AR2. And if you're in the type of setting where you think that your time series data has this autoregressive correlation structure to it, and you have to select the order of the autoregressive process, you can use the data to select the order using some type of algorithm that will find the order that has the best information criteria, like an AIC or something like that. And that's what I'm going to do over here in the simulation results I'm about to explain. So I'm going to look at some autoregressive processes, use the data with an information criteria like AIC to pick the order, and then I'm going to do a goodness of fit test. So this is our other type of hypothesis test we're thinking about. for the coefficients test, we saw that the method is biased in a way that makes us think things are more significant than they really are. So let's see what selection bias can do for goodness of fit tests. There's a type of test we would do in this scenario called a lung box test. So I'm going to do AIC to pick the order of the regression model, and then the lung box test to see if that model fits the data. So in the top density plot here, you can see the blue line is the null distribution of the test statistic, and the shaded area is the density of the test statistic over many simulations. So the fact that the shaded area matches the blue line is good in this top panel, because in this top panel, this is when the information criteria selects the correct order. So we're doing a goodness of fit test. We want to see if this model fits the data. And this is the case where the model does fit the data. So we want the goodness of fit test to match its null distribution. And it does. Great. The problem is, in this bottom part, this is when the information criteria selects the wrong order. So this is when we have the wrong model. In this case, we want the goodness of fit test to actually reject the null hypothesis. We would like to see this shaded region be larger than the blue density curve. We want to see values of this test statistic which are large, because the null hypothesis is false. Instead, what we see is that the test statistic still matches the null distribution, even though the null distribution is false. So what this is telling us is that exactly when we select the wrong model, our test can't tell us that we selected the wrong model. The reason for this is, again, because this goodness of fit test was designed under the assumption that the model would be chosen without using the data. So if we use the model, if we use the data to choose the model and then do the test, we're breaking that test. So the goodness of fit test can't tell us that the model doesn't fit. So to summarize these examples, if we're thinking about significance of predictors, then when we do model selection, our standard inference methods are going to be anti-conservative. They're going to tell us, yes, those predictors are significant. This makes sense because our model selection algorithms are usually looking for which predictors seem most predictive. And then our test statistic is kind of checking how predictive is this predictor. Similarly, for goodness of fit tests, we have this selection bias, but it goes in the opposite direction. Instead of being anti-conservative, it makes goodness of fit tests conservative. And this also makes sense because the goodness of fit test is asking if the model fits the data. And if we used the data to pick the model, then we're finding the model that fits the data best. So then when we check for goodness of fit, the test is just going to tell us, yes, it fits, even when we pick the wrong model. Okay, so this might seem just kind of like a obscure statistical, mathematical, theoretical concern. Is it really important? And I would say yes. I think this is one of the important factors behind a pretty important and impactful problem, which is often referred to as a reproducibility crisis. And this is a quote, this is a passage from a paper in the open science collaboration called Estimating the Reproducibility of Psychological Science, where they tried to replicate 100 different studies in 3 psychology journals. And what they found was when they tried to replicate the findings of these studies, only about 40% of the effects were rated to have replicated the original result. So this is telling us, the point of this paper is that there is something like a reproducibility crisis, where we have results being published in peer-reviewed journals, and when people try to replicate those results, they can't. They don't get the same result. So that's a problem. We're using statistical methods because we're hoping that these statistical methods will only give us publishable effects that are reproducible, and then when people try to reproduce them, they're not able to do so. So I think that this selection bias could be one of the main reasons why this is happening. People are using their data set to pick which effects to test, and then they find the effects that look significant, and they publish them, just like in our candy example. But then when someone else tries to replicate the finding on a new data set, the effect was already chosen, so they're no longer going to have data that makes that effect look significant. So then now when they test it, it no longer looks as significant. Okay, so at this point, some of you are thinking, we have a standard way to solve this, right? This is a well-known problem in machine learning when we refer to it as overfitting. So we have a solution method. We use data splitting, right? We use different subsets of data to fit our model, to choose our hypotheses, and then some other validation set to evaluate the model, test its goodness of fit or significance, and so on. And this is just an example where I'm illustrating this on a data set which has 240 lymphoma patients and about 7,400 genes. And the outcome variable is a survival time variable. So in this type of a setting, you could do a Cox proportional hazard model. But because there are more predictors than outcomes, we have to do some type of regularization. So we can do a Lasso penalized Cox proportional hazard model. And the GLMNet package in R can do this for us. So that's what I've done here. And the interesting thing about all this is it's just a few lines of code to separate my data into training and test sets, fit a model, use cross-validation to figure out how much to regularize it. The model ends up picking, or I should say the Lasso Cox pH model ends up picking 15 genes as being predictive. And then if we use our test data set to give us inference for those predictors, this inference over here will actually be valid. It will not suffer from this selection bias. And that's because the data we use to form these test statistics was a different subset of data than the data we used to decide those were the tests we wanted to do. So this is just an example of data splitting applied to a sort of interesting problem. And data splitting is great when we can do it. It's pretty straightforward. Like that previous slide showed basically all the code that I had to use to do that entire result. And it works often without making any types of assumptions. I might have to make assumptions for the other methods I want to use to work. Data splitting is fairly assumption-free. And it's going to work in most settings almost automatically. So, for lots of problems, data splitting is the way to go. And I certainly am not trying to make sure everyone uses the R package I'm here to talk about today. But in some settings, data splitting won't work, or it might not be the best way to solve this selection bias problem. So one issue with data splitting is that it can affect reproducibility. If we're going to choose random subsets of the data for training and test splits, then someone can sort of, even without intending to, try more than one split and end up going with the result that gives the most impressive looking conclusions. So they might not even be intending to do that themselves. They might have just run the code once and they're changing the way the plot looks or something when they run it again. And if people aren't thinking very carefully, they might not realize that they can override the intention of data splitting by trying it multiple times. And if someone else wants to reproduce your result, they might need to use, for example, the same random seed to get the same split of data. So there's some reproducibility issues with it. It also doesn't use all of the available data. So if you have a small sample size, like in this previous example, 240 is not that large of a sample size, especially when we've got more than 7,000 predictors. So maybe data splitting isn't the best idea to solve the problem for this data set. Maybe we would prefer to use all 240 observations to fit the model. If we could, then we'd like to use the same data set to do the inference. And that's basically the solution method that I'm about to discuss will allow us to do. There are also some problems where it's just not feasible to do data splitting. For example, there could be some dependent structure in the data, like time series data or network data, where it's harder to figure out how to split it into independent subsets. So what I'll talk about instead of data splitting is a conditional probability approach to dealing with the selection bias. There are a few papers here which are sort of some of the earliest papers in this area. And to motivate this, why we would use a conditional probability, let's think about another very simple example. So let's think about the example where we just have many independent effects and we want to apply a screening rule, which is a thresholding rule. We're only going to look at those effects which are above some cutoff. The ones which are below this cutoff are kind of, we don't have enough time or resources to look at everything. So we're going to first do this screening. So what I'll do is I'll look at only those effects which are above 1. Now, once they've made it through my selection rule, I need to determine how I want to test their significance. The red line here is the standard normal density, and we know we can't use that because here all of these effects are actually coming from the null. They have a 0 mean, and so the observed screened effects don't line up with the standard normal. We kind of saw previous examples of that, and this is just another one. But what they do line up with is the conditional version of this distribution. If we condition on the fact that they're bigger than 1. So for this problem, conditioning on them being bigger than 1 is the same as truncating them below at 1. So this curve here, you can see it lines up pretty well with the simulated effects. If we use this green curve to decide what's significant, then we would control type 1 error again. So that's the basic idea of this conditional approach on a simple enough example where we can sort of plot the distributions and understand what's going on. One way of thinking about this intuitively is that an effect has to surprise us once to be selected, and then conditional on being selected, it now has to surprise us again to be considered significant. And we're going to apply this same intuitive idea in various different settings. And the key thing to remember is that we just have to take the null distribution of our test statistic and condition it on the selection rule. So some notation to sort of define what error probability notion we're controlling with this procedure. We call this the selective type 1 error. And what this notation means is it's the probability of making a type 1 error because it's computed assuming the null is true. So what's the probability we reject the null, given that it's true, under some model, conditional on that's the model we selected using the data. So we take the null distribution and then we condition it on selecting that model. So we construct tests to control this conditional type 1 error, which we call selective type 1 error. And several things there are several nice properties about this definition that help motivate it. One is that it reduces to the standard definition of type 1 error, the classical one, if the model is chosen a priori. So if your model selection rule is that you deterministically were going to use model lowercase m, then this condition is deterministic now, so it just goes away. So it reduces to the standard definition if in the case when you didn't use the data to pick the model. Data splitting also controls this type 1 error because for the same reason. This conditioning here depends on a different independent set of data than the test statistic. So the conditional distribution is the same as the unconditional distribution in that case. So in both of these cases, you can just delete the conditional part and this definition reduces to the standard one. So data splitting controls this, and it's the normal definition if we didn't use the data to pick the model. But in general, when we have used the data to pick the model, we have to figure out how the null distribution for the test statistic is affected by this conditioning. And we see in many examples that the way it's affected is that it becomes truncated to a certain region. So this is from one of the previously mentioned papers. This is illustrating the selection region for the Lasso. So if we're using the Lasso algorithm to pick variables in our model, it turns out that the event that you pick a certain subset of variables can be written as a affine inequality in your outcome variable y. And what that means is that in Rn, the outcome space, there is a union of polytopes, the shaded regions here. What these shaded regions represent are all of the outcome variable values which would have led you to pick the same model. So you're going to have some observed value of your outcome variable, y, and the fact that you've selected this model means you know that y is in the shaded region. So now we know we can condition on selecting this model by truncating the distribution of y to the shaded region. So this is the geometry involved in applying the selective type 1 error idea to models selected by the Lasso. It turns out that this property here, the affine inequality, characterizes a lot of different model selection algorithms, forward stepwise as well. So there are many model selection algorithms where we can apply the same basic ideas to conducting the conditional inference. Okay, so to show this in action, I'm using functions in the selective inference package now. And what I'm going to do here is I'm going to generate the data myself so I know what the true coefficients are and all that. So I've got 100 observations, 200 predictor variables. The first 5 predictor variables are actually non-zero. So it's a very sparse true model. The other 195 of them are just 0. And what I'm going to do here is I'm going to generate a vector of outcomes, a matrix of predictor variables, and a vector of predictor coefficients. And then I'll plug this data, synthetic data, into the LAR algorithm function. The LAR algorithm is just a particular algorithm that will find Lasso solutions. So all this is going to do is use the Lasso to pick some predictor variables out of those 200 variables. And then I use this LAR inference function to calculate the conditional inference, conditional on selecting the given variables. And what I see here is that the algorithm chooses variables 1 through 5, but it also puts in variable 188. That's pretty impressive because it found the 5 correct variables out of all 200. That's good. And it didn't put in too many other ones which were incorrect. And then I've got a column of p-values here. And I can see also for the one variable which was a mistake that shouldn't be included in the model, the p-value for that one is not significant. So I also like that. And then the other thing that I see is that for the ones that were selected, they're not all significant. And what this is reflecting is that there's a reduction in power. So we have less significance. These p-values are not as small. But that is necessary because, like I said before, these effects have to surprise us a second time in order to be declared significant. They surprised us once in order to be included in the model. So if these p-values were all very small, then maybe that testing method would not control the conditional type 1 error. So I hope this just kind of illustrates a basic use of this package. And you can see that you can fit Lasso models and then get valid p-values for the predictor variables in those Lasso models. And the other thing I should have mentioned about this is For the lasso, you have to choose how much regularization to do. And what I've done here is I've used the AIC criteria to pick the number of variables. That's a little unusual. People often use cross-validation with the lasso, but you can use the AIC criteria. And there are various options in this package for which criteria to do. Another way is to just use a specific value of lambda, the regularization parameter. So here, if you're going to use one specific value of lambda to get one lasso fit, then you can use the function fixed lasso inference at that value of lambda. And here we have smaller p-values. So we have less of a loss of power when we're just looking at one specific value of lambda rather than choosing it optimally. The AIC chose it optimally. Okay, and this plot here is just showing the lasso coefficients as a function of lambda. So what I've done here by picking one specific value of lambda is I'm sort of taking one vertical slice of this and saying these coefficients are my current estimates. There's one other more kind of recent development to help improve power in these tests. I'm going to actually skip this though. And the last thing I'll mention is that one of the drawbacks to this approach has to do with the reduction in power. And a lot of this reduction in power is due to conditioning on too much in some sense. We condition on the model, the selected model, but in order to compute p-values, we sometimes have to use these ad hoc tricks to condition on more things in order to make the computation simple. And so that extra conditioning can reduce power. And there's a method to try to get around that and improve power by fitting a randomized version of the lasso. So you can think of this as sort of adding noise to your response variable in some sense. If you do this, then the event that you select a given model is no longer truncating the distribution of your original outcome. It's truncating the noised version of it, but the original outcome is not fully truncated. And it turns out that that tends to help with the power of these tests. This part of the package is not quite as user-friendly yet. Hopefully we're in a future version of the package make the interface with these functions a little more user-friendly. There's one thing that I kind of swept under the rug a few slides ago, which is that I told you that I was fitting the lasso at a fixed value of lambda, but in fact, the value of lambda that I used had a plug-in estimate of the variance of the noise. And I got that plug-in estimate using cross-validation, basically. So it turns out that if you do this, then the selection event is not really an affine selection event. So there's a little bit of hand-waving that goes on in doing something like a plug-in estimate here. It's a similar sort of situation to the situation with Gossett and Fisher, where people were using plug-in estimate for the standard error, and Gossett figured out that you needed to use the t-distribution instead of the normal distribution as a result. So there's a similar sort of thing going on here. And there's some good news, which is that we have methods of getting around this. One of them is to use the square root lasso instead of the lasso. The square root lasso does not square the error. So instead of squared error, it's now just the regular 2 norm of the error. And what that does is that means that both the error part and the penalty part have the same order to them. And so you don't actually need to know sigma, the variance of the noise, to pick a good value of lambda, the regularization parameter, when you do square root lasso. So this is an advantage of square root lasso. And it means the takeaway is that we can use a value of lambda which is picked without looking at your outcome variable y. And then that means we're now back in the setting where we really have an affine selection event, and we're not doing this hand-waving plug-in thing that I mentioned previously. The bad news is that this is not yet in the R package. There is Python code for it, though, on our GitHub repository. So if you wanted to use this, if you're willing to do it in Python, that's already done. One other approach to getting around this problem of having to use the data to pick lambda, this is where I'm going to plug my own specific research, is that the model selection event does not have to be an affine event. We can also deal with quadratic selection events. And it turns out that using cross-validation to pick a given Lasso model is a quadratic selection event. So that's the good news. And the bad news is that tends to have very low power because cross-validation uses the data very exhaustively. So when we condition on using cross-validation, we end up conditioning away a lot of power. Okay, so just to wrap up with some conclusions, there are some other complementary R approaches with R packages as well. So there are Bayesian approaches to dealing with this question of trying to use Lasso to get a sparse model, but also give inference. There are a number of approaches that are based on de-biasing your original estimate. You use your penalized regression technique like Lasso to get a biased estimate of beta, and then you do something to de-bias that and you apply asymptotic normality. So there are a number of approaches that apply that sort of technique. And then there's an approach called POSI, or for post-selection inference, which gives a simultaneous inference guarantee over all possible submodels, which is a very robust type of guarantee. It's very strong, but that means this is also a fairly conservative and computationally intensive procedure. So this procedure, I don't think they have code yet that can get beyond, for example, like 20 predictor variables, because you have to do a best subsets search to apply this. If you're interested in goodness of fit tests, there's also the RP test package by Rajan Shah and Peter Bielman, which can do goodness of fit tests in high dimensional regression. And I have some forthcoming research where we might end up giving a similar functionality to the selective inference package. So just to give the high-level takeaway messages once more, using the data to decide which inferences to conduct results in selection bias. And we have various names for this problem, depending on what community we come from. You can either overfit, or you can be anti-conservative or conservative, depending on what type of test you're doing. If you can't apply data splitting for some reason, or you don't want to, you have alternatives. And the selective inference conditional approach is one. This package is on CRAN. You can find it. You can download and start fitting the Lasso and getting p-values. And then there's these other packages that you could try as well. So that's it.
I've got a question on how does all of this interact with the whole ML causal inference, so like double ML, this sort of stuff where you often don't see the selection going on, but there's definitely selection going on. There's a lot of sparsity that's induced by kind of double ML procedures that we'll never see. Another place to see this a lot is in covariate or instrument selection. You've got very high-dimensional instruments, you have very high-dimensional possible confounders on using ML to select which ones.
Do you want the usual discount or do you want an
necessarily create bias, but that's not going to be and our inference. So should I like throw out all my knowledge of what's going on in that?
All right, because that'll be easier.
No, a great question, by the way. It's an area of active research that various people have different sorts of questions and approaches. One thing to think about is that often when you're doing causal inference, it means that you have one particular variable, your treatment, which you know you're going to do the inference for. So you're not actually worried about a selection bias on choosing to test the treatment itself. But what you might want to do if you're in a high-dimensional regression setting is choose which things to control for. And there are approaches. That's the double ML problem. But one aspect of that is, since you're not choosing what the target is, you don't have to worry about the selection bias of the test at the target. You have sort of different things to worry about than exactly what the topic of this problem was. But like the whole point of double ML is trying to address what problems arise in that particular setting. And there are also versions of the double ML problem which are more directly connected, where you might, for example, not know which interactions of the treatment variable with other effects that you want to test. So you could think about testing for heterogeneity by interacting your treatment variable with some subset group variables and use the data to pick which of those you actually want to report inference for. And then you could be in exactly this sort of setting. And you might want to use these sorts of tools to do that. But yeah, it's just stepping back from those. It's a good question where it's something I've thought about, but I don't have any ongoing work on, but there are a number of people who do. Yeah.
So we're talking about the counts for the data splitting. So there's one that represents the initial So that's the point for a cross-validation, right? So we have pre for cross-validation, we don't have enough sufficient data, we do it before, and then we can get a distribution for the metrics like AUC or whatever. So that's the point of it.
Yeah, so you can make data splitting more efficient with cross-validation, for example, by switching which of the two subsets you use for selection and inference. An issue you have to deal with then is stability, because the model selection algorithm can be unstable, and you could deal with you get different models selected on the different subsets. So then you've got to address the fact that you're no longer going to be interested in one specific regression model with one particular subset of predictors that were chosen. You might have different subsets of predictors chosen across the different folds or something like that. And so you've now got to start dealing with model instability and think about things like model averaging and so on. And actually, that is the focus of one of the alternative methods here called stability selection. So stability selection is in the title of a paper about this, and the authors of that paper have this package, but some other people also implemented a package doing the same thing. So these two packages here will do something like that. So they'll do cross-validation. They'll actually use that model instability to aggregate models together and use the sort of like how often a predictor variable is included in a given model as the notion of stability and the stable set. And yeah, so that's a good point, and it's very closely related to one of these complementary approaches.